Alright, in this video I'm going to be working a couple of problems that are dealing with pipes, both open-ended pipes and closed-ended pipes, and we're going to be looking at how the frequency and wavelength are related to the length of the pipe. And for each of the examples we're going to assume that the speed of sound is 343 meters per second, that the temperature is appropriate for the speed of sound to be that in the air. Okay, so I'm going to work three different problems, and hopefully these three will be sufficient to help you with whatever assignment you have dealing with these. Alright, so the first question, the lowest note a flute can play is a middle C, which is 261.6 Hertz. Assuming that the flute is open at both ends, the mouthpiece and then the far end, solve for the length of the flute. Alright, so we know that it is an open-ended pipe. Right? The flute is a pipe that it's going to be open at both ends, which means that our equation is going to be this one, that the frequency is equal to some integer, which is the harmonic, times the velocity of the sound divided by 2 times the length of the pipe. Alright? Now, since this is the lowest note that the flute can play, then we're going to assume that it's the lowest frequency or the longest wavelength. That means it's going to be its fundamental. And if you'll remember back when we did strings, the fundamental meant the longest wavelength possible, okay, which is the lowest harmonic, which means that our N value here will be 1 because we're going to look for the first harmonic, which is the fundamental tone. So let's go ahead and put the frequency in, which is going to be 261.6 Hertz, which is going to be equal to 1, since it's the fundamental, which will be the lowest harmonic, times the velocity, which will be 343, divided by 2 times L. Okay, so from there we should be able to mathematically work this out. Divide both sides by 1, so we have 261.6 equals 343 over 2L. Now from here there's a couple of different ways that you can do it. I'm going to multiply both sides by 2L, and by multiplying both sides by 2L I will end up with that I have 523.2 times L will equal 343. Then we'll divide both sides by 523.2. Divide by 523.2, and we'll get that the length of the flute is 343 divided by 523.2, 65.6, so 0.656 meters, which is reasonable. That should be about the length of a flute. And so there we go. There's one problem. All right, let's look at another one that has a different frequency, a different harmonic. Okay, so now we're looking at an organ pipe. An organ pipe is going to be open at both ends. All right, and it tells us that it's producing a sound at its fourth harmonic. It gives us the frequency of that fourth harmonic. So again, since it's open at both ends, we're going to use the same equation as before, that the frequency is equal to the harmonic, or this N integer, times the velocity over 2 times the length of the pipe. Alright, so now we're going to put in the numbers that we have. We know it's the fourth harmonic, so N is going to be 4. We know that the velocity of sound in air is 343, and then it gives me the frequency, which is 283. So this one mathematically is going to work out very similar to the last one that we did. So 283 is equal to 4 times 343 over 2L. Alright, so we'll divide both sides by 4, and that gives us 70.75 is equal to 343 over 2L. Okay, again we'll multiply both sides by 2L, and that will give us 15, carry the 1. So 141.50 L is equal to 343. Divide both sides by 141.5. And we get 343 divided by 141.5 And our answer is 2.42. Right? So the length is 2.42 meters. Awesome. So there you go. That's the length of the organ pipe. Not too bad, huh? All right, let's look at one more question. All right. This one is going to have a closed-in pipe. All right. So we have a tube of air open only at one end. Okay, so this one's going to be closed and then open at this end. All right. And so then we've got that it has a length of 1.8 meters. Okay, length equals 1.8 meters. The tube sustains a standing wave at its fifth harmonic. What's the distance between one node and the adjacent antinode? Okay, well first let's go through and let's find the wavelength and the frequency. Okay, so we know again that the frequency is going to be equal to the harmonic times the velocity divided by 4 times the length, right? This is the equation for the closed end, is it's divided by 4L because we're looking at the quarter wavelengths. Okay, now again, with a closed end, the harmonics can only be odd, and so we have a fifth harmonic, which means the n is going to be 5. Okay, so the frequency is going to be equal to 5 times the velocity, which is 343, divided by 4 times the length of the pipe, which is 1.8. So we can solve for the frequency. So 5 times 343 divided by 4 times 1.8. Okay, and we get 238. Okay, so the frequency is 238 hertz. Once we have the frequency, then now since we're looking at the distance and we want it to be wavelengths, we know that velocity is frequency times wavelength. Okay, so 343 equals 238 times the wavelength, so divide both sides by 238. So 343 divided by our previous answer, which will be 1.44. So that tells us that the wavelength is 1.44 meters. All right, now the question is, what's the distance between one node and the adjacent antinode? Well, an antinode is the exact opposite of what a node is. If you'll remember, if we have a standing wave, which is something like this, and then probably then repeats itself on the other side, right? A node are these positions where there's no vibration, no movement, right? An antinode then is the place where you have the maximum movement, where these points are moving all the way up and down. So an antinode can either be a crest or a trough. Those are all going to be the situation where it's moving the farthest. All right? So we already know that from one node to the next is half of a wavelength, right? Because you need to go through a little bit more to get the full wave. So this is a half a wavelength, which means from a node to an antinode is half of that, which is then a quarter of a wavelength. So since the wavelength is 1.4, if we divide that by 4 and find a quarter of it, we get 0.36, and so 0.36 meters is the distance from one node to the adjacent antinode. And so once you have these basic ideas, then you understand the numbers that are required for the open pipe and the closed pipe. And since you've done such a good job, we give you the crazy chicken. Awesome. Cool. Thanks for participating, and I hope that this is enough to help you with whatever you're working on. Night.